Identification and verification of quadratic equations. Welcome, everyone. Let's begin our session by revisiting what we already know. In our previous lessons, we established the fundamental rule that a quadratic equation must follow the standard form of a subscript x squared plus bx plus c equals 0, with the crucial condition that it is not equal to 0. Now, here is the challenge. In many real-world mathematical problems, equations aren't always handed to you in this neat, organized, standard form. They can be quite tricky. They might be hidden behind parentheses, tucked inside fractions, or even masked by higher-degree terms that look more complex than they actually are. Because of this, you cannot simply take an equation at face value. To truly verify whether an equation is quadratic, we must go through a systematic process of simplification. Over the next few slides, I will show you exactly how to strip away these layers to reveal the true nature of the equation. The process of verification. Now that we understand that quadratic equations aren't always presented in that perfect, standard form we saw on the first slide, let's look at a reliable roadmap you can use every single time. To determine if an algebraic equation is truly quadratic, you shouldn't guess. Instead, follow these 4 systematic steps. Step 1 is expansion. If you see any parentheses or brackets hiding within the equation, your first task is to break them open. You'll do this using the distributive property or by applying algebraic and algebraic identities. For instance, when you see a plus b squared, you should expand it to a squared plus 2, a b plus b squared. Once everything is expanded, we move to step 2, simplification. This is where you tidy up the equation by combining all like terms. This means you should group all your x squared terms together, all your x terms together, and all your constant numbers together. Next, in step 3, we perform standard form alignment. To see the true structure of the equation, you need to move every single term to one side of the equals sign so that the other side is exactly 0. This is crucial because it allows you to clearly see if the equation matches our target form. A x squared plus bx plus c equals 0. Finally, we reach step 4, the final degree check. This is the moment of truth where you identify the highest power of the variable x. If, after all your hard work simplifying, the highest power is exactly 2 and the coefficient a is not 0, then you can confidently conclude the equation is quadratic. However, if the x squared term has disappeared, or if the highest power is something else entirely, then it is not quadratic. Keep this process in mind, because in the next slide, I'll show you some common traps where students often skip these steps and reach the wrong conclusion. Critical pitfalls in identification. Now that we have established the systematic 4-step process for verification, I want to warn you about a very common pitfall. As I mentioned in the previous slide, you cannot simply look at an equation and make a snap judgment. Students often make the mistake of deciding if an equation is quadratic just by glancing at it, but you must be cautious of certain scenarios. Let's look at our first major trap, apparent quadratics, which I like to call fake quadratics. These are equations that look like they contain an x squared term at first glance, but if you actually perform the simplification steps we just discussed, the x squared terms cancel each other out entirely, leaving you with nothing more than a linear equation. Let's walk through a concrete example together to see this in action. Suppose you are asked to verify if the following is a quadratic equation. The quantity x plus 1 all squared equals x squared plus 5x plus 2. If you just looked at this, you might see that x squared on the right and immediately think quadratic. But let's follow our steps. First, we must expand the left side. Using our algebraic identity for a binomial squared, we expand the quantity x plus 1 squared to get x squared plus 2x plus 1. Now our equation looks like this. X squared plus 2x plus 1 equals x squared plus 5x plus 2. Next, we simplify. If we subtract x squared from both sides of the equation, notice what happens. The x squared terms vanish. We are left with a much simpler equation. 2x plus 1 equals 5x plus 2. Now, following step 3 from our process, we move all terms to one side to set the equation to 0. By subtracting 5x and 2 from both sides, we arrive at negative 3x minus 1 equals 0. Finally, we perform our step 4, the final degree check. Looking at our simplified result, the highest power of x is now just 1. The x squared term has been completely eliminated. Therefore, our conclusion is that this is actually a linear equation, and definitely not a quadratic equation. Keep this in mind, because in the next slide, we will see the exact opposite problem. Equations that look even more complex than this, but actually hide a quadratic within them. Apparent higher degree equations, the hidden quadratics. Now let's shift our focus from the fake quadratics we just discussed to something slightly different. Hidden quadratics, or what we call apparent higher degree equations. In the previous slide, we saw how an equation might look quadratic but actually simplify into a linear one. Here, we encounter the opposite scenario. These are equations that look much more intimidating at first glance. They might appear to be cubic, meaning they have a degree of 3 or even higher. However, as we apply the systematic verification process we learned in slide 2, the higher degree terms actually cancel each other out, leaving us with a perfectly valid quadratic equation. Let's work through a concrete example together to see this in action. I want you to verify if the following equation is quadratic. X multiplied by the quantity x squared plus 3x minus 2 equals x cubed plus 5x minus 10. At first glance, that x cubed term makes it look like a cubic equation, right? So, let's follow our steps. Step 1. Expansion. We need to expand the left side by distributing the x into the parentheses. When we multiply x by x squared, we get x cubed. X times 3x gives us 3x squared, and x times negative 2 gives us negative 2x, so our equation now looks like x cubed plus 3x squared minus 2x equals x cubed plus 5x minus 10. Step 2. Simplification. Notice that we have an x cubed on both sides of the equals sign. If we subtract x cubed from both sides, those terms cancel out completely. This leaves us with 3x squared minus 2x equals 5x minus 10. Step 3. Standard form alignment. To see the true nature of this equation, we need to move everything to one side so that the right side equals 0. Let's subtract 5x from both sides and add 10 to both sides. This gives us 3x squared minus 2x minus 5x plus 10 equals 0. When we combine our like terms, the x terms, we get 3x squared minus 7x plus 10 equals 0. Step 4. Final degree check. Now let's look at our result. The equation is now in the standard form, a x squared plus bx plus c equals 0, where a equals 3, b equals negative 7, and c equals 10. Because our coefficient a is not 0, and the highest power of x is exactly 2, we have reached our conclusion. Despite how it looked initially, this is, in fact, a quadratic equation. As we move into the next slide, keep this in mind. Never let a high power like x cubed scare you away before you've finished your simplification. Real-world application example. Imagine you are working on a landscaping project, designing a rectangular garden. You have determined that the length of this garden is x plus 5 meters, and the width is x minus 2 meters. You are also given a specific target. The total area of the garden must be x squared plus 3x plus 10 square meters. Your task here is to verify whether the relationship between these dimensions actually forms a quadratic equation that we can use to solve for x. Let's break this down step by step, just as we practiced in the previous slides. First, we must establish the mathematical relationship. We know that the area of a rectangle is found by multiplying length by width. So, we set up our equation as x plus 5 all multiplied by x minus 2 equals x squared plus 3x plus 10. Step 2 is the expansion phase. Using the distributive property, we multiply the terms in the brackets. When we multiply x by x, we get x squared. Then, we multiply x by negative 2, and 5 by x, and 5 by negative 2. This gives us x squared minus 2x plus 5x minus 10. After combining our like terms, the left side simplifies to x squared plus 3x minus 10. So our equation now looks like x squared plus 3x minus 10 equals x squared plus 3x plus 10. Next, we move to step 3, standard form alignment. To see the true nature of this equation, we need to move everything to one side so that the right side equals 0. We will subtract x squared from both sides, subtract 3x from both sides, and subtract 10 from both sides. As we perform this, notice something interesting. The x squared terms cancel each other out completely, and the 3x terms also cancel each other out. We are left with negative 10 minus 10 equals 0, which simplifies to negative 20 equals 0. Finally, we reach the verification step. Looking at our result, all of our variable terms, both the x squared and the x, have vanished. We are left with a mathematical impossibility, or a contradiction, where negative 20 is claimed to equal 0. Therefore, our conclusion is clear. This specific relationship does not form a quadratic equation. Now that we have looked at the theoretical pitfalls of fake and hidden quadratics, let's apply everything we've learned to a practical, real-world scenario. As we move into our final slides, keep this in mind. Always be wary of equations that seem complex at first glance, as the true degree of the equation is only revealed after you have finished all your simplifications. Common mistakes to avoid. First, let's talk about premature judgment. This is perhaps the most common mistake. I see students do this all the time. They glance at an equation, see an x squared term, and immediately label it as quadratic. Please do not do this. As we discussed in our step-by-step verification process earlier, you must always simplify the equation fully before making a decision. An equation might look quadratic at first glance, but as we saw in our earlier examples, the quadratic term might vanish once you expand the brackets. Second, watch out for incorrect expansion. When you are performing step 1 of our verification process, be very precise with your algebraic identities. A frequent error is expanding something like x plus a squared as simply x squared plus a squared. In doing so, you are forgetting that crucial middle term, which is 2x. If you miss that middle term, your entire simplification will be wrong, and you'll end up with an incorrect verification. Finally, do not ignore the condition that a must not equal 0. This is a vital rule. If, after all your hard work simplifying, you end up with something like 0x squared plus 5x plus 2 equals 0, you might be tempted to say it's quadratic because it looks like the standard form. However, because the coefficient of the x squared term is 0, the quadratic nature has disappeared, leaving you with a simple linear equation. Remember, for an equation to be truly quadratic, the coefficient, a, must be a non-zero real number. Now, before we wrap up our session and move into our final summary, I want to pause and discuss some common pitfalls. As we have seen through our various examples of fake and hidden quadratics, it is very easy to fall into certain traps if you aren't being careful. Keep these 3 points in mind, and you will avoid the most common errors in identification. Key takeaways. All right, we have reached the end of our lesson. Before we wrap up, let's review the key takeaways to ensure you have a solid foundation for your upcoming problems. First and foremost, remember, simplify first. As we saw in our earlier examples with brackets and distributions, you should never try to identify the degree of an equation at a glance. Always expand your brackets and combine all like terms before you make any decisions. Second, keep this gold standard in mind. An equation is quadratic if and only if it can be written in the form a times x squared plus b times x plus c equals 0, provided that the coefficient, a, is not equal to 0. This is your ultimate checklist. Third, always watch for cancellations. As we discussed in the section on fake quadratics and hidden quadratics, be very alert for any x squared terms or even higher powers that might cancel each other out during the simplification process. If the x squared term disappears, the quadratic nature disappears with it. Finally, remember that the degree is final. The true nature of the equation, whether it is linear, quadratic, or something else entirely, is determined only by the highest power of the variable remaining after you have completed the full simplification process. If you follow these steps systematically, you will avoid the common pitfalls we've covered today. Great job working through these slides with me.